All right, so welcome back everybody. What we're doing today is a continuation of our chapter 28 discussion. This will be the last part of the chapter 28 lecture. And so what we need to do next is talk a little bit more about the Biotsavart Law because we just sort of briefly introduced it in the last lecture. We haven't really used it yet or really stated what it is. So let's get into that. So the Biotsavart Law is a way of calculating a magnetic field. Much like Ampere's law, that's something you can use it for. You can use it to calculate a magnetic field. But the way it works is very different. We think about calculating a magnetic field by breaking it into little infinitesimal pieces and then integrating over all of those pieces to get the total magnetic field. So the Biotsavart Law says that an infinitesimal magnetic field at a point in space, dB, is created by an infinitesimal bit of electric current somewhere else. Okay, so if you have a little bit of current, you get a little bit of magnetic field. That's the idea. So dB is what we call this infinitesimal bit of magnetic field in the Biotsavart Law. So what it says is dB is equal to mu naught times I times dl crossed r hat divided by 4 pi r squared. Okay, so there's a lot going on there. Obviously, we need to break it down. First, look at the diagram. What you see is a wire that carries a current I, and the wire is very long, but the current element is just a tiny little bit of that overall current. So just take a little tiny piece of that wire, and the vector dl is pointing in the direction that current is flowing. Okay, so think of the dl vector as giving you a little bit of that overall path that our current is flowing along. It's pointing in the direction of our conventional current. Okay, also in this diagram, you have this vector r. It points from that current element to the point P. So point P is where we're trying to calculate the magnetic field. And r just takes you from the current element to the point in space P where we want to calculate the magnetic field. Okay, now r hat is a unit vector. Whenever you see a little hat on top of a vector, that means it's a unit vector. It has length 1, in other words. And which direction is this pointing? Well, it's just pointing in the direction of r. So it's a unit vector which takes you from the current element to the point P. Now notice how on top in the Biotsavart Law we have dl cross r hat. So we're crossing with this unit vector r hat. Okay, on the bottom in the Biotsavart Law, you just see r, which doesn't look like a vector at all. It's just a scalar. This is the distance between the current element and the point P. So you can think of it as the magnitude of the vector r, just giving you the straight distance from the current element to the point P. Okay, so then we have dB. We can calculate it that way. But again, all that gives you is an infinitesimal bit of the overall magnetic field. What we need to do is integrate over all the different current elements to give you the total magnetic field at point P. So that's a lot to do. So we need to see some examples so we get a sense of how to use this. And so the first example I'm going to give you here is how can we apply the Biotsavart Law to an infinitely long thin wire. I want to know what the magnetic field due to an infinitely long thin wire actually looks like. So here's what we have. In the picture, you have a wire. It's going straight up. It's carrying a current going straight up. And we want to know what the magnetic field is at some point near the wire. So that point is shown. It's a distance d away from the wire. So in the Biotsavart Law, we have this dl vector. So the very first thing on our diagram that we should put is the dl vector. Again, this is a little infinitesimal current element, so it's just a little bit of the overall current, and it's pointing as a vector in the direction that current is flowing. Okay, so I'm just going to draw that dl vector there so we can refer to it later. What's next? My r vector. Okay, so my r vector takes me from the current element to the point in space where I'm trying to calculate the magnetic field. Okay, so now we have dl and r. We're in good shape. Okay, so the next thing I want to get some kind of handle on is what is the direction of dB? what direction is the magnetic field at that point? Well, in the Biotsavart law, we have a cross product of dl and r hat. I know that in general, I can use the right-hand rule to figure out how a cross product works in terms of what direction it's going in. So here's what you do. Take your right hand, you point your fingers in the direction of dl. Okay, then so now your right hand, the fingers should be pointing straight up in the direction of dl. The next thing you do is you curl those fingers in the direction of r. So you should be curling them to the right in the direction of r. Now your thumb should be pointing into the page. So that's the point. Using the right hand rule, dB is going into the page. And as it turns out, it doesn't matter which current element we pick, they're all going to give us a dB that's pointing into the page. So all of these different magnetic fields that we're going to integrate together are going into the page. That's what we learned by using the right hand rule. Okay, so the next thing is, I'm going to figure out what the magnitude of that dB is. Okay, because dB is a vector, has a direction to it. We just figured out that's into the page. And it also has a magnitude. So we're dealing with a cross product. Okay, so let's first factor out everything that's just a scalar that doesn't have anything to do with the cross product. We have mu naught times I divided by 4 pi r squared. So let's just move that to the front. Okay, the next thing we have to deal with is we're taking dl cross r hat. Remember how cross products work. You take the magnitude of the first vector, you multiply that by the magnitude of the second vector, and then you take the sine of the angle between the two vectors. Okay, so we have the magnitude of dl, then we have the magnitude of r hat, but r hat is a unit vector, so its magnitude is 1 by definition, so we're going to put in 1 for the magnitude there, and then we'll have sine of theta. Now notice on the diagram, I'm showing you theta, the angle between dl and r. That's shown right there. We need to know what that angle is. Okay, so what's next? Well, here, when I talk about dl, I'm talking about a distance in the y direction. Okay, so let's call that dy just because we're talking about a distance in the y direction. What else can we say? Well, r, which appears on the bottom in the Biotsavart law, remember that's just the distance between my current element and the point in space where I'm calculating the field. I have a nice right triangle here where on one side of that triangle I have the distance d. That's how far away from the wire my point is. Then I have the distance y, this vertical distance, which tells me how far away from that line is my current element. So r, which is just the distance, again, between that current element and my point, is the square root of y squared plus d squared. That's just the Pythagorean theorem. That's how we got that. All right, what about sine of theta? Because that appears in my Biotsavart law equation. Well, let's think about this right triangle we have right here. Okay, so sine is opposite divided by hypotenuse. The opposite side is d, and the hypotenuse is r. So sine of theta is just going to be d divided by r. And of course, we just said r is the square root of y squared plus d squared. So we can think of sine of theta as d divided by the square root of d squared plus y squared. That's how we can write this. Okay, so that was a lot. Let's kind of regroup and figure out what we have. For the magnitude of dB, remember we have mu naught times I divided by 4 pi r squared. But what I just did here is I subbed in for r the square root of d squared plus y squared. Okay, so I'm just subbing in for r what we said earlier. Okay, next I have dl, but I'm just thinking of that as dy for the time being, so just like a little distance on the y-axis. And then finally we have sine of theta, which we can make the substitution that sine of theta is d divided by the square root of d squared plus y squared. Okay, so that's what we have so far. And that can be simplified quite a bit. The first thing I'd like to do here is just pull out everything that's constant and put that in the front of the expression on the left. So what are the constants? We've got mu naught, we've got I, we've got d, and then on the bottom we have 4 pi. Those are all constants. Those are not changing. On the other hand, we have on top a dy, and on the bottom, since we have the square root, we've got 3 factors of that. That's the same as the 3/2 power. We have d squared plus y squared to the 3/2 power. That's how we can write this in a more simplified way. Okay, so to recap, we use the Biotsavart law to write down what the infinitesimal bit of magnetic field is at this point P. The next step is we need to integrate over all of these current elements until we've covered everything. Okay, so there's our dB expression from the previous slide. It hasn't changed at all. I need to integrate over all of those dBs to get the total magnetic field at the point in question. So the total field B is the integral over all of my dBs. Okay, so in this integral, I'm going to pull out the constants mu naught I times d over 4 pi, just like we said before. Those are constant. And what variable am I integrating over? Well, I'm integrating over y. And since my wire is infinitely long, that means my limits of integration are going to go from y equals minus infinity to y equals infinity. That's the integral I need to do. So here, I'm not going to work out the integral. This is actually shown in my handwritten notes that I upload to Canvas. So you can take a look at how this works out. But for now, I'm just going to tell you the result. If you do that integral, you're going to get 2 divided by d squared. Okay? So I'll take the constants out front, which are mu naught times I times d over 4 pi, and multiply that by 2 divided by d squared. Okay, so a number of simplifications. We can cancel out the 2. That gives us 2 on the bottom. We've got d on top. We've got d squared on the bottom, so we can just say that's a factor of d on the bottom. And now we have mu naught times I divided by 2 pi d. Okay, that should be looking familiar. This is the same exact expression that we got when we used Ampere's law. So I'm just trying to show you here that we've got 2 different methods to calculate a magnetic field, Ampere's law and the Biotsavart law, and it gives us the same answer. Now, admittedly, this one is a little bit more complicated than Ampere's law, but keep in mind that Ampere's law can only be used in certain special situations. So there are other cases we'll see where we can only do a problem using the Biotsavart law. We can't also use Ampere's law. All right. So I want to call back to something from the very beginning of the semester where we used arguments from symmetry to show that a certain part of the electric field, maybe it's Ex or Ey, some component of the electric field goes to 0 due to symmetry. We have a similar situation here with magnetic fields, where we can argue that because of symmetry, one or more components of a magnetic field are going to go to 0. So here's the situation. I have a circular loop of current with a radius of r, and that lies in the xy plane. The center is at the origin. Okay, so the current is just going in a circular loop in the xy plane as shown right there. Let's consider a point P that's on the z-axis. My question for you is, which components of the B field at that point are going to be 0? I want you to do this by making an argument from symmetry. So consider 2 current elements, that's dl, on opposite sides of the loop, and try to figure out how their magnetic fields are going to add together. Okay, so work this out and see what you come up with. Okay, so this is a picture of the current loop that we're talking about, but now we're looking at it completely edge on. Okay, so the loop, this is what we look at when we see it edge on. Over here, we have a current which is coming straight out at us, but then when we follow it around, now the current over here is going into the page. Okay, so the current on this side is coming out of the page. the current that we see on this side is going into the page. That's what it looks like to see this thing edge on. So this I'll call DL1. This is a little current element on this side of the loop. And this I'll call DL2. That's a little current element on the other side of the loop. Okay? Now, since I'm interested in the magnetic field up here at point P, which is on the z-axis, what I need to do is show a vector going from each current element to that point. So if I look at a vector going from this current element to that point, that's what I call R1. So this will be R1 hat. That's just a unit vector going in this direction. And over here, if I have a vector going from my second current element to that point, that's going to be R2. So if I draw R2 hat, that's just a unit vector, again, going that way. So let's remind ourselves what the Biotsavart Law says. dB is equal to mu naught times I. And then we take dl cross r hat. And then we divide by 4 pi r squared. The part of this that I want to focus on is dl crossed with r hat. Let's figure out what the dB vector is for this current element. So what kind of magnetic field does this contribute? And what's the dB vector for this? What is the magnetic field that this one contributes? And the way we're going to think about it is using the right-hand rule, because we can get the direction of dB by doing the right-hand rule. So let's do it over here first, okay? We have to take dl, which is going out of the page like this. We have to cross it with r hat, which is going up and to the right like this. Okay, so take the right hand and point your fingers out of the page. That's in the direction of dl. And then you have to curl the fingers of your right hand in the direction of r hat 1, like this. So now your thumb is pointing like this. So it's pointing kind of up and to the left. That's going to be our vector dB1. I know it has to be perpendicular to this, by the way, because when you cross two vectors, you get something that's perpendicular to both vectors that you crossed. Okay, over here we have dl2. I need to cross that with r2 hat. So dl2 is a vector going into the page. So point the fingers of your right hand into the page. Then if I curl the fingers of my right hand in the direction of this r, my thumb is now pointing up and to the right, something like this. And that's dB2. Again, I know there's a right angle right there. So the argument from symmetry is basically this, okay? For every component of dB that is perpendicular to the z-axis, so like x components or y components, we have an opposite component contributed by a little current element on the other side, which exactly cancels it out. So basically, all components that are perpendicular to the z-axis will cancel. So that means my B field in the x direction, that's 0. My B field in the y direction, that's also 0. That's what we get by making this argument from symmetry. Now it's pretty clear that at the end of the day, we're still going to be left with a B field in the z direction. So for that, we have to just calculate it. There's no way around it. All right. So in the previous example, we saw how in this situation where you have a current loop in the xy plane, you have some point on the z-axis, that we get a magnetic field that only points in the z direction. So the x and y components of this magnetic field go to 0. With that established, let's find an expression for what that magnetic field is. So we know it's only in the z direction, but what's the formula or the expression that gives us the magnetic field? Okay, so now we're going to take a look at this same kind of current loop, and a point on the z-axis where we want to find the magnetic field, and we're going to calculate what it is. So remember from before that all the components except for z are going to cancel. So when we do this calculation, we only need to focus on the z direction. Okay? So just like before, what we're going to have are a few things. We're going to have a little current element. So let's pick a current element on the right side. Let's say it's going into the page, and we'll have dl represent a vector giving us that current direction. Okay, the next thing is if I connect that current element to the point in question, this will be r. And so r hat is just a unit vector, again pointing in the direction from the current element to that point. Okay, now let's put an angle here. It's going to come into play later, so we'll call it phi, just to give it a name. And let's do the right-hand rule one more time, just so we're straight with this. If I take dl going into the page, and I cross it with this r vector, then my thumb is pointing up and also to the right like this. That is dB. Okay, so that's that little piece of magnetic field that I'm eventually going to integrate over. But remember, we only care about the z component of dB. So I only care about this piece of it, which I'll label as dBz. And how am I going to figure out what that component is? Well, a few things. This right here is a right angle. And this is the same as the angle phi that you see down here. So if we're only interested in the z component, dBz, well, that's just the magnitude of dB. And this is the adjacent side of our triangle. So we take cosine of phi to get the z component. Okay, so if I know the magnitude of this dB vector, and I take cosine of that angle phi, then I've got myself the z component. Okay? Okay, good. So let's label a few other things here. This distance between the center of the loop and my point is z. Okay, so that's just how far along the z-axis we go to until we get to the point. Over here, this is just the radius of the loop, so that's capital R. Now, this distance between this current element and the point that I'm showing you is lowercase r. Okay, so lowercase r tells us how far away the current element is from the point where we're calculating the B field, just to remind you. Okay? So just from the geometry of this, lowercase r is the hypotenuse of a right triangle, one you see right here, where the two legs of the triangle are z and capital R. So if we take z squared plus r squared under the radical, then we'll get this distance lowercase r. Also, using that same triangle, we can figure out that cosine of phi, well, it's the adjacent side of this triangle. The adjacent side is r, capital R. And the hypotenuse is lowercase r. Okay, so that's the cosine of the angle. Okay, so that means I can write the cosine of the angle like this. It's big R divided by square root z squared plus big R squared. Or I could write that as the 1/2 power. I'm talking about a square root. Okay, the next thing is we need to remember how the Biotsavart law works. dB is equal to mu naught I times dl cross r hat over 4 pi r squared. Okay, that means the magnitude of dB, which by the way is something we want to know from up here, is equal to mu naught times I. That's divided by 4 pi r squared. And And then we're doing dl cross r hat. So really, if I'm getting the magnitude of dB, I just want to know the magnitude of this cross product dl cross r hat. So the magnitude of any cross product is the magnitude of the first vector, which is dl, okay, times the magnitude of the second vector, which is r hat, and then sine of the angle between dl and r hat. So I want to convince you of something. So dl is going into the page like this. That's the way the current is going, okay? And r hat is going like this, which is sort of on the page itself, up and to the left. Now these two vectors are at a right angle. Okay, so if I have one vector in the plane of the page and another vector going into the page, there's a right angle or a 90-degree angle between those two. Okay? Okay, so let's take this a little bit further. We've got mu naught times I divided by 4 pi r squared. Now, the magnitude of dl, I'm just going to leave that as is. But the magnitude of r hat, that's a unit vector, so that's 1. And sine of 90, that's also 1. Okay, so let's put this all together, right? For dB z, okay, for the z component of this magnetic field, we've got the magnitude of dB, which we have over here is mu naught times I divided by 4 pi little lowercase r squared, magnitude dl. Okay? And we take that and we multiply by cosine of phi, which we have over here as big R divided by this, well, here, it's big R divided by little r. Let's just write it that way for now. Okay, so we've got mu naught times I divided by 4 pi. We have little r to the third power down here. Okay, that's what we have. And then we have big R on top. Okay, so the last thing, oh yeah, and then we have magnitude dl. Can't forget that. Okay. So the last thing I'm going to do here is I'm going to rewrite lowercase r as the square root of z squared plus big R squared. So on top I have mu naught times I times big R divided by 4 pi times z squared plus big R squared. Now if I have the square root and I take that to the third power, that's the same as saying the 3/2 power. And then we'll have magnitude dl. Okay, there it is. There's dB right here. So I ran out of space. So make sure you have this down. And I'll erase this entire board and we'll finish up the calculation. Okay, so to recap, the last thing I wrote down there was dBz is equal to mu naught times I times big R divided by 4 pi times z squared plus big R squared to the 3/2 power times the magnitude of dl. Okay, that is a lot to think about, I won't lie, but let's take a look at what we have, okay? Now all of this right here, mu naught, I, big R, and z, these are all constants. So you can at least be thankful that we have nothing but constants here. And that means if we want to figure out what Bz is, the magnetic field in the z direction, all I have to do is integrate all my dBz's. And in that integral, I have nothing but some constants, which I can immediately pull out to the front. So I have mu naught times I times big R divided by 4 pi z squared plus big R squared to the 3/2 power. All those constants come out. And the only thing left in my integral is dl. So if I integrate over all my dl's, what am I really getting? I'm just getting the total distance around this loop of current. And the total distance around this circular loop of current is the circumference. That's 2 pi r. Okay, big R. So, okay, I'm going to have 2 pi on top, 4 pi on the bottom, and I'm going to have 2 factors of big R on the top once I incorporate this factor. So mu naught times I r squared is on top. And on the bottom, I'm just left with 2 times z squared plus r squared to the 3/2 power. Okay, that is our magnetic field for a current loop when we're on the z. Okay, so again, x and y components are both 0. The z component, which we just found, is mu naught times I times r squared divided by 2 times r squared plus z squared to the 3/2 power. So I want us to take a closer look at the expression we just derived for the magnetic field due to a current loop on the z-axis. So in particular, I want us to think about what happens when z becomes much, much greater than r. So in other words, your distance away from the center is getting really big compared to the radius of the loop. This is just another way of saying we're far away from it. So let's just look at the expression here in the bottom, where we have z squared plus r squared to the 3/2 power. Okay? So another way we could write that is we could take a factor of z squared out of this parentheses, and so we'll have 1 plus r squared divided by z squared. Okay? And that whole thing is taken to the 3/2 power. Okay, so first, let's think about this. If I have z squared, and then I take that to the 3/2 power, what I'm really dealing with is z to the third, z cubed. So let's pull out z cubed, and then what I'm left with in these brackets is 1 plus, and then I have r over z, and that's being squared to the 3/2 power. Okay, but the point is, if z is really, really big compared to r, then the ratio of r divided by z is a really small number. And if I square it, it's going to be even smaller still. So really, what we see here in the brackets is approximately equal to 1, because we're just taking 1 plus a tiny number. It's basically the same as 1, okay, to a good approximation. So approximately, what we're dealing with is just z to the third power. Again, as long as z is really big compared to r, then this basically boils down to z to the third power right here, which means bz is approximately equal to, we got mu naught times I times r squared divided by 2 times, this is becoming z cubed. Okay, so this is true as long as z is much bigger than r. So, in other words, if z becomes much, much bigger than r, so our distance on the z-axis is much, much bigger than the radius of this loop, that's what it means to be far away, then approximately bz is equal to mu naught times I times r squared divided by 2z to the third power. So let's take a look at this. Z is what tells us how far away from the loop we are, and the magnetic field is getting weaker as z increases, but it's not an inverse square law. It's not a 1 over z squared type dependence. It's actually what we call an inverse cube law. So the magnetic field gets weaker as z cubed as opposed to z squared, which is what we saw for electric fields. Okay, so that takes us to this idea of a magnetic dipole. Now, I just want to point something out here. The B field produced by a current loop, kind of like what we saw in the previous example, is actually very similar to a bar magnet, which has a north pole and a south pole. Now, we haven't fully worked out what the B field due to a current loop is everywhere. We just sort of saw what it looks like if you're on the z-axis. But if you do map it all out, you're going to find that those B field lines look really similar to those produced by a bar magnet. And so, because a bar magnet has two poles, we call it a dipole. Because this current loop is so similar to a bar magnet, we also call that a dipole. And so we can just briefly describe what these magnetic field lines look like. If you notice in the picture, we see the magnetic field lines going up through the center of the current loop, and then curving back around, and all the way around until they go back up into the current loop. So the magnetic field lines are actually closed loops that go in and then back out of the current loop. Okay, so what we just found is that for a magnetic dipole, the B field doesn't follow an inverse square law. It instead follows an inverse cube law, because as you get further and further away, the B field strength falls off like 1 over r cubed instead of 1 over r squared, as we've seen in the past. Okay, so there's one last point to make here, and that is that a magnetic monopole doesn't exist. So what do I mean by that? You can't take the north pole of a magnet or the south pole of a magnet and just isolate it. So for instance, what if I had a bar magnet with a north and a south pole and I cut it in half? You might say, okay, well, in one hand I have the north pole, in the other hand I have a south pole, but actually that's not true. If you cut a magnet in half, you just create two new magnets, each one which has its own north pole and south pole. So you can't have a magnetic monopole where you just have a north pole and a south pole by itself. Those actually don't exist. They don't exist in nature. All right, so let's do some more examples with the Biotsavart law. Here we have a wire that's bent into a half circle of radius r, and it carries a current of I through it. Then we have two long straight wire segments that connect the circular segment as shown in the picture. What we want to do is give an expression for the magnetic field at the center of that half circle. Okay, so at the point labeled C. All right, so next, what we're looking at is this situation here, where we have a straight segment of wire, a half circle segment of wire, and then another straight segment of wire. And I really want to break it down into those three pieces. So the current is going to the right. That's what we're seeing in the diagram. So let's take a little current element on the straight segment of wire over here. And let's call this our DL, but let's label it DL1. And this is the point where we want to know the magnetic field. So remember, the R vector goes from your current element to that point. So it's going to be pointing just to the right. So this would be, let's call it R hat 1. Okay, the next thing is, if we're on the curved segment of wire, let's draw a little current element on this part. Okay, so our DL vector is going to go along with the current. Let's call that DL2. And then the R vector is going to be pointing from the current element to the point. So this will be R2. And then over here, we have the last little current element that I want us to think about. So this is going to the right. That's the way the current is moving. There's DL3. And then the vector R3 goes from this current element to the point. So it's actually moving, or it's actually pointing backwards to the left. And here is R3 hat. Now, the reason we care about all of this stuff is the Biotsavart Law involves these vectors dl and r hat. So in particular, we have dB is equal to mu naught times I. And then we have up here dl cross r hat over 4 pi times r squared. Okay, so immediately I want to convince you that dB1, that has to equal 0. If I'm taking the cross product of this dl vector and this r vector, they're pointing in the same direction. Whenever you take the cross product of two vectors that are pointing in the same direction, you're guaranteed to get 0. In other words, cross product depends on sine of the angle. So if you take sine of 0 degrees for two vectors going the same way, you're going to get 0. So that's why we know dB1 is 0. So this is not contributing any magnetic field from this straight segment of wire. The same exact argument can be made for this third segment, because the dl vector and the r vector are exactly opposed to each other, so there's a 180-degree angle between them. Again, in a situation like that, when you take the cross product of two vectors going in opposite directions, you always get 0. So this segment of wire is also not contributing anything to our overall B field. On the other hand, if we look at this curved segment, we can get a sense that there is a B field there that we need to think about. So if we take dl, which is going up and to the right like this, and then we cross it with our r vector, so I'm going to point my fingers in the direction of dl and then curl them in the direction of this r vector, then my thumb is going to be pointing into the page. So dB, the magnetic field contributed by this little current element, so I'll actually call that dB2, is pointing into the page. Okay? All right. So 1 and 3 we can ignore. We're going to focus our attention on 2. So the next thing we're going to do here is think about the magnitude of this vector, dB2. So what is that telling us? Just telling us how much magnetic field is being contributed by this second current element that we drew in the diagram. So we have mu naught times I, and on the bottom we have 4 pi, and then we have little r squared. And remember what this represents. This is the distance between your current element and the point in question where you're calculating the field. So this should be uppercase R, because that's what we're using for the radius of this loop. So every single current element on this curved part is just one radius away from the center. That's the idea. Now, we have a cross product next, and when we take the magnitude of a cross product, the way this works is we have the magnitude of the first vector, it's dl, we have the magnitude of the second vector, r hat, and then we have the sine of the angle between them. Over here, it should be pretty clear that we have a right angle between the dl vector and the r vector. So 90 degrees. And of course, sine of 90 is 1. Also, here, let's just write that here. Sine of 90 goes to 1. The magnitude of r hat is also 1 because it's a unit vector. So dB2, that magnitude, that's equal to, we've got mu naught, we've got I, we've got 4 pi times big R squared on the bottom, and then here we have the magnitude of dl. Okay, and then the other two terms, again, we're just going to 1. All right, what's next? Well, I need to find, if I want the total B field, I need to basically integrate over dB2. Again, the other current elements don't really contribute anything to this, so we just need to focus on dB2. And the nice thing about this is it's pretty simple. All of this here out front are constants. We have mu naught, we have I, and then we have the radius of this loop, so it's all constants out front. Pull those out. So mu naught times I divided by 4 pi big R squared. And then in the integral, we have just dl and nothing else. So what does it mean when we integrate over, sorry, I should say dl2. That's the one we're talking about. So what does it mean to integrate over all the dl2 vectors? Well, it's just to take the total distance around this curved part, which is half a circle. So half a circumference is pi times big R. So half the circumference of this thing is half of 2 pi r, so just pi times r. All right, so we have a pi on top from here. We have a pi on the bottom, those cancel. We also have a factor of r on top from this, and then we have 2 factors of r on the bottom. So when it's all said and done, we're going to have just 1 factor of r on the bottom. So the magnetic field from all of these different currents is mu naught times I over 4 times r, and the direction is into the page. We found that at the beginning. It's going into the page. All right, so there's actually another way to work that problem out that I want to show you, and it uses the result from the one we did just before that, where we have a loop of current like this, and we calculate the magnetic field at some point on the z-axis above the center, just like this. So what we found there was the magnetic field was equal to, mu naught times I times r squared divided by, then we have 2 z squared plus r squared to the 3/2 power. So that's a general expression for the magnetic field at this point above the z-axis for this loop of current that looks like this. Okay, so in our case, we're dealing with z is equal to 0. So in other words, we're right at the center of that loop of current. So if we set z equal to 0, then we get mu naught times I divided by r squared divided by 2, and then, okay, I just have now r squared to the 3/2 power because z is going to 0. So really this is just r to the 3rd power. Okay, now if we simplify, we've got mu naught times I divided by 2 times big R. Now what that's telling you is, what is the magnetic field at the center of a current loop? Okay, but we don't have a full current loop in this problem. We have half of a current loop. So it stands to reason that the magnetic field due to half of a current loop should be, well, half as strong as if we have a full current loop like this. Okay, so if we have a half loop, then just take 1/2 of that, which is mu naught times I, divided by 4r. Hey, that's the answer we got a second ago. So we can really think of it as we just are in the center of a current loop and just cut the strength of that magnetic field in half because we only have half of a current loop. We'll get the same answer. Okay, so what we found is that the B field is equal to mu naught times I divided by 4r, and it's going into the page. Okay, so here's the question for the class. I want you guys to try this out. So in this picture, you have these 2 half circles which are connected. One of those is radius r1, and the other is r2. So they're connected by these straight wire segments to form a full complete loop. We're given here that r1 is equal to 2.5 centimeters, r2 is equal to 7.5 centimeters, and the current that's running through this loop is 3.65 amps. Okay, so we're going to need to know mu naught for this calculation, so it's right there, 4 pi times 10 to the minus 7. What you need to do is find the magnetic field, both the magnitude and direction, at that point labeled C. All right, so here's what we're dealing with in this problem. First, we have a half circle segment of wire. I'm labeling that segment number 1 up here. Down here, the one I'm labeling is number 2, is another half circle. It has a bigger radius. And then these 2, 3, and 4 are these straight segments of wire which connect everything together. So I want us to be reminded of the Biotsavart Law, which is dB is equal to mu naught times I times dl cross r hat divided by 4 pi r squared. Okay, so if I want to get some kind of sense as to what the magnetic fields being contributed by each segment are, I just need to think about dl cross r hat. So if we look at it for segment number 1, the one way I could draw the dl vector is like this. So if I choose this as my current element, for instance, then my dl vector, which I'll call dl1, is kind of going up and to the left, whereas my r1 vector points from that current element to this point in the center where we're trying to get the magnetic field. Okay, so if we do the right-hand rule, okay, dl goes like this. So you point the fingers of your right hand in the direction of dl, and you curl them like this in the direction of your r hat. Your thumb is pointing out of the page. Okay, so whatever magnetic field we're getting from that first segment, it's out of the page. Okay, so what if we do segment number 2? So this would be one of the current elements. Let's call that dl2. Okay, a vector pointing from that current element to that point is r2, or r2 hat for the unit vector. And okay, if we do the cross product, just do the right-hand rule. We have dl going this way, curl my fingers in the direction of r, and then my thumb is pointing once again out of the page. So these two magnetic fields, B1 and B2, they complement each other. They're both going the same way, so we'll add them together. On the other hand, if we look at, let's say, the magnetic field B3 or B4 for that matter, they're both going to be 0. And just to show you the reason for that, let's say I look at the current element over here on segment number 3. So my dl is going this way in the direction of my current, call that dl3. But my r vector is going the opposite way, pointing from the current element to this point. Whenever you have two vectors that are in opposite directions, so they're anti-parallel, or they're in the same direction, they're parallel, the cross product goes to 0. So that's going to be the case for these two straight wire segments. Okay, now as for what the magnetic field contributed by these half circles looks like, we saw in the previous problem that if you have a half circle carrying a current, the very center of that circle, the magnetic field is given by mu naught times I divided by 4r. So this is what we found previously. But the thing is, we have two magnetic fields that look like this to add together. One of them is mu naught times I over 4 times r1, and the other is mu naught times I divided by 4 times r2. So that's what we have to do. So there's a common factor that we can pull out, which is mu naught. By the way, mu naught is 4 pi times 10 to the minus 7 Tesla meters per amps. Now the current, which again is a common factor to both of these terms, what was our current again? Let's see. Oh yeah, 3.65 amps. Okay, and then we'll just divide that by this factor down here, which is 4. So that's another common factor. Okay, so next we have 1 over r1, and r1 was 2.5 centimeters. So here, let's write that as 0.025 meters. And our 2, the bigger one, was 7.5 or 7.5 centimeters. So we'll have 1 divided by 0.0750 meters to convert that unit as well. That's what we need to calculate. Crunch these numbers, we get the strength of the magnetic field. And what it comes down to is 6.12 times 10 to the negative 5 Tesla. And again, the direction is out of the page. Okay? So that's how we do this one. Okay, so the next topic here is magnetic materials. And what we want to get a sense of here is if you have something like a bar magnet and it attracts another bar magnet, how does that actually work? Because so far, we've really only talked about magnetic fields created by currents running through wires. So how does a magnetic material actually work? And I mean, the actual simple answer is it works the same way as what we've seen in the past. An electric current creates a B field. So what does this look like on the macroscopic level? Well, we have currents running through wires and they create magnetic fields. We've seen different ways to calculate them. We have Ampere's law, we have the Biotsavart law, but the basic idea is a current running through a wire creates a magnetic field. That's also true on the microscopic level, okay? So think about how inside of atoms, we actually have electric currents, okay? Electrons are moving around inside of atoms in various different ways, and when an electron moves, that's an electric current. If you have moving charge, you have an electric current. So you're producing a tiny little B field. Okay, so let's talk, really briefly and without diving into the details too much. How do electrons move inside of an atom? So at the bottom of the screen there, you see a simplified model of an atom where you have a nucleus with a positive charge and an electron with a negative charge moving around the nucleus. Now, in a rough sense, you can think of the electron as orbiting the nucleus, kind of how a planet orbits the sun, and at the same time spinning on its own axis, kind of how the Earth spins on its axis as it orbits around the sun. The real picture is much, much more complicated than that. You need quantum mechanics to really fully understand how electrons move within atoms, but this picture is good enough just to picture how we have electric current in an atom. Okay, so that's how you get tiny little currents in atoms. Those can give you tiny little B fields in a material. Now, in some materials, these B fields are all pointing in random directions, so they don't really add up to anything. They just all sort of cancel out. But in a magnetic material, in a magnet, the B fields are all lined up. And so they actually add together to give you a large-scale B field. So let's take a closer look at that. Now, when we have the electrons spinning and orbiting, these types of motions that happen within an atom, we can kind of model that, or we can conceptualize that as a tiny little current loop, because of course, if an electron is moving around in a circle, that's a little loop of current. If an electron is spinning on its axis, we can also think of that as a little loop of current. And we've seen that this is what we call a magnetic dipole, right? It's really similar to the B field produced by a bar magnet with a north and a south pole. All right, so I want you to remember something that happens when we have a magnetic dipole, so a little loop of current, in an external B field. Okay, so this is something we talked about way back in chapter 27. If you have a magnetic dipole in an external B field, it feels a magnetic torque. So it's going to be twisted. It's going to be made to rotate. So take a look at the picture at the bottom of the screen. We have a little current loop, and the direction of that current is shown by I. Now, remember how this works. We take our right hand and we curl that in the direction of the current, and your thumb should now be pointing straight up. That's at the direction of our mu vector, okay? That's called our magnetic dipole moment. That's the mu vector. It's pointing straight up. Then, if we want to know what the torque is, we take mu cross B. So again, do the right-hand rule for this cross product. First, put the fingers of your right hand straight up in the direction of mu. Then take those fingers and curl them in the direction of B. Which direction is your thumb pointing? It should be pointing into the page, indicating a torque going clockwise. Okay? So in other words, this current loop that we see, if we put it in a B field, is going to be feeling a torque going clockwise. That's going to make it line up with the B field lines. Okay? So that's really the takeaway point. If you have a little current loop, it wants to line up with whatever magnetic field you put it in. It's feeling a torque in that direction that makes it line up with those B field lines. So let's talk about ferromagnetic materials. Okay? A ferromagnetic material is something that consists of these tiny little domains. They can be anywhere from about 0.1 to 1 millimeters in size. And within that domain, all of these electron spins are lined up. So what are some examples of ferromagnetic materials? Well, iron is a ferromagnetic material. So is cobalt, so is nickel. These all have this sort of property. And what if we take a ferromagnetic material that starts off unmagnetized? Okay, so take a look at the diagram of an unmagnetized ferromagnetic material. It's unmagnetized because all of the different domains are pointing in different directions. So they're not all lined up. They're all just sort of randomly pointing in different directions. So they don't actually add up to give us any kind of strong magnetic field because they're all pointing in random directions. If we take this, though, and we put it in an external B field, so if we apply a really strong magnetic field to this thing, well, as we saw, all these magnetic domains are going to want to line up with it. Okay, they're going to feel a torque, which makes them want to line up with this external magnetic field. So now, when we've magnetized it, all of these domains are pointing in the same direction. And now what we have done is we've magnetized the material. Okay, so this is how you make a bar magnet. Basically, you just take some chunk of iron or cobalt or nickel, you put it in a really strong magnetic field, you magnetize it, and now you've got a nice bar magnet. Now, once you magnetize something, it's not going to stay that way forever necessarily. There's a way to demagnetize the material. And one way we can do that is by heating it up. Okay, so if you take something that's been magnetized and you heat it up to a really, really high temperature, all of these domains are going to be jiggling around at higher and higher speeds. And these thermal motions can actually just randomize the alignment of those domains. So they can go from nice and organized and everything is pointing in the same direction. If you heat it up, they can just now be pointing in completely random directions again, and now you've demagnetized the material. Okay, a little bit more on this. We saw in some previous examples that if you just have current running through a wire, it's really hard to create a very strong magnetic field if that's all you have, right? Even to get to like 1 Tesla, you have to run some ridiculous amount of current through a wire to get to that level of magnetic field. And that's where electromagnets come in. So here's what an electromagnet is. It's just a coil of wire that's wrapped around some kind of ferromagnetic material. Usually we just use iron for this. And we run some current through that wire. Now, what happens? When you have current running through the wire, that creates a magnetic field. Because you have this magnetic material in the presence of that magnetic field, all of the domains are going to want to line up with that magnetic field, and that just makes the magnetic field even stronger. It enhances the strength of the magnetic field. And you might wonder, well, how much can we enhance the strength of a magnetic field just by putting, like some iron in the middle of it? Well, it's actually surprising. You can increase the strength of the B field by hundreds of thousands of times, like 10 to the 5 times stronger. Let's say if you have a solenoid with an iron core in there compared to just empty space in there. So if we want a stronger magnetic field, putting some kind of ferromagnetic material inside instead of just empty space inside of a solenoid is a really good way to do that. And then lastly, in terms of sort of technological applications, we have magnetic data storage. Okay, we can use ferromagnetic materials to store data. And this is done in a number of ways. We have audio tapes and videotapes. Some hard drives work this way. If you have a credit card, it has a little magnetic strip on it that stores the data for your account. Now, the way this works is we have magnetic domains. They can be facing one way or another, maybe up or down. And we can use that to represent in binary code a 1 or a 0. Okay, so maybe if a domain is facing up, that's a 1. If it's facing down, that's a 0. If we have a whole bunch of these domains all in one place, we can store a whole lot of 1s and 0s, and we can store a whole lot of data. And so what do we do if we want to write some new data onto a hard drive, or maybe read some data out from a hard drive? Typically, this can be done with an electromagnet. So if I have an electromagnet really close to one of these magnetic domains, and I apply a really strong magnetic field next to one of these domains, well, I can change it. I can have it say, if it's facing down, I can have it flip up. And if it's facing up, I can make it flip down. I can sort of change what's going on in each domain if I just apply a magnetic field to it. So that's what's happening in this animation here. You see that there's this right head, which is sort of scanning along these different magnetic domains, and it's changing the value as it goes along. Okay, so this is how we read out data. This is how we write data as well. So that's really it for this lecture. There are some practice problems at the end, as always. You can go through those if you want the extra practice. So I'll see you in the next one. But in the meantime, as always, stay healthy out there. Take care.